So in this video we will see how to convert from decimal number system to any other number system with base b. In the last lecture we have seen about how to convert a number into the decimal number system. So in the last video we have seen about how to convert a given number into the decimal number system, from a given number to this decimal number system. In this video we will see how to convert from decimal number system to any other number system with base b. The general process to convert the decimal number into the given base is by continuous division of the given decimal number with the base value of the desired number system. This is what we have to do, and the division process should be continued till the remainder is not less than the base itself. So we have to keep on dividing till the time our remainder does not gets less than not the remainder, the quotient does not get less than the base value, and the remainders should be noted down in the reverse order. So after dividing the decimal number system with the base, we have to see what is the quotient and what is the remainder. So we will keep on recording the quotient and the remainder and note them down separately. Now after noting them down separately, we will again divide the quotient, and we will keep doing this process till our quotient does not become less than the base itself. The record of the remainders will be later on used to represent the number in the desired number system. The remainders should be written in the reverse order. That is, the remainder which is obtained after the last division will be treated as the MSB, that is the most significant bit, or the bit with highest weight, whereas the remainder which is obtained after the first division will be treated as the LSB, or the least significant bit. Least significant bit means the bit with minimum weight or the lowest weight. This procedure is useful for converting the integral part of the number, whereas the fractional part, to convert the fractional part, we have to multiply it with the base. So we will see that how to convert the any decimal number, any given decimal number to any given decimal number system to any other number system in the desired base. So we will understand the process with the help of example. So in this example we can see that suppose we have to convert the given decimal number system, which is 13.375, into the binary equivalent. So how to do this conversion? To do this conversion, we will separate the integral part and the fractional part. First, we will take the integral part, which is equal to 13. Now, as the procedure we laid down in the last slide, we will divide the decimal number 13, the integral part of this complete number, the given number, by the base of the number system in which we want the answer. So, as we want the answer in the binary number system, therefore our base will become 2. Dividing 13 by 2 will give you the remainder as 1. So, we note down the remainder and also the quotient. So, the quotient becomes 6 and the remainder is 1. Now, as the quotient is greater than the divisor, we have to again divide the quotient by the divisor. Now, if we divide the quotient 6 by the divisor 2, we get the new quotient as 3, whereas the remainder is 0, because 6 is an even number and it is completely divisible by 2. So, our remainder is 0. Now, if we further divide this 3 with our base system in which we want the number, which is 2, so we get the quotient as 1 and the remainder also as 1. Furthermore, now we cannot divide this 1 with our base 2, because this quotient 1 is now less than our divisor. So, we stop dividing the quotient and we note down this particular quotient, whichever is left at the last. Now, when we have to denote this 13, which is the decimal number, into the binary notation, so we will start noting down the number from in this order from here. So our this one will become our MSB, whereas this one will become our LSB. So the binary equivalent of 13 will be 1, then 1, 0 and 1. So 13 will be represented in binary as 1, 1, 0, 1. So this becomes the 1, this one becomes the MSB and this one becomes the LSB. So we have to note down it in the reverse order. Now moving on to the fractional part, what we have to do is we have to take the fractional part first. So this fractional part is 0.375. Now this 0.375 is to be multiplied by the quotient, by the base in which we want our new number. So the number we want in binary number system. So the quotient, so the base becomes 2. So the radix we have to multiply the given fractional part, which is 0.375, with the base. So multiplying 0.375 with 2 gives 0.75. Now this 0.75, 0.75, from the 0.75 we will take 0, because the integral part is 0, so we will write this 0 separately. So this 0, which is we got this 0 from here, so this is this 0. Now after taking this, whatever is left, we again will multiply it with the base. Now if we will take 0 from this, so still the remaining number is 0.75. Again we multiply this 0.75 with our radix, which is 2, so we get 0.5. Now, in this case, we have we have 0.5, sorry, multiplying 0.75 with 2 will be equal to 1.5. So our 1.5, so from this 1.5, 1 is the integral part. So that integral part should be returned separately, whereas the fractional part of 1.5, which is 0.5, will be again taken, and this part 0.5 will be multiplied with the base again. Now, after multiplying this 2 with 0.5, what we get is 1.0. So, 1, which is the integral part, should be returned separately, whereas the fractional part, which is nothing, now it is 0, so it should be noted down here. So 0. So we have to multiply it until we get this as 0 or the condition up to which we have to find. So if it is given, if in the question it is asked to find the answer up to second place of decimal, so then we have to find the answer accordingly. Else, if nothing is said, then we have to keep on multiplying it till the time the fractional part becomes 0. So there are two cases. So in this case, the fractional part became 0, so we stop multiplying. Now this binary equivalent of this 0.375 will be 0, 1, 1. So here we don't have to note down in the reverse order, but we have to note down in the general order. So the general order will be 0, 1, 1. So 0.011. So the binary equivalent of 0.375 will be equal to 0.011. Now, in the question, the total number given was 13.375. So, the binary equivalent of 13.375 is nothing but the sum of the number, the binary equivalent which we obtained earlier for 13, which was equal to 1101. So 1101, and this is the fractional part. So we have to write them together. So writing them together will give you the total binary equivalent of the question given. So the question was 13.375 in base 10. So the answer will be 1101.011 in base 2. So this is the general procedure to convert a decimal number into the given base. So you have to remember that the given decimal number should be divided with the base, and the reminders in the integral part should be noted down in the reverse order, whereas in the fractional part we have to continuously multiply with the base and note down the integral part separately, whereas the remainder fractional part has to be continuously multiplied till we get the fractional part as 0, and then we have to note them down together to get the complete answer. So this is the general procedure. Now we'll see the same thing with the help of another example. So now the question given is, the number given is 73.75, and we have to convert this 73.75, which is given in the decimal number, into octal number. So the octal equivalent has to be found. So octal means 8. So the base of the new number system is 8. Now to find the number in base 8, we have to divide the given number, the integral part of the given number, with the base. So we take the integral part of the number, which is 73. So 73 when divided with 8 is 9s. So 8 9s are 72. So 72 and 1 is remainder. So we note down this 1 separately. So 1 becomes our remainder, and now 9 is our new dividend. So now this question becomes our new dividend, and we have to again divide it by the divisor. Dividing it again by the divisor 8, we get 1 as the remainder, which is noted here, and the quotient is also 1. Now this quotient is less than the divisor, so we cannot divide it any further. So this quotient is written here again. And now the new quotient is 0 because nothing is left. Whatever was left, we have noted it down here. So after noting it down, we have to denote this 73, we have to write it in the reverse order. So we have to start from here, then this number should become our MSB, so 1. Although in this case you can see that the order is 111, so if you write it in either of this order or this order, it will be correct, but you should keep this in mind that this becomes your MSB and this becomes your LSB. So this should be this reminder should be noted down first, whereas this should be noted down at the last. So this is our MSB and this is our LSB. So the octal equivalent of 73 is 111. Now comes the fractional part. So in the fractional part, what we do is we take 0.75, the fractional part of the given number. So that is to be multiplied with our radix, the radix in which we want the answer. So multiplying this with radix 0.75 into 8 gives us 6. So 6.0. So now you see, after the first multiplication, our fractional part becomes 0 and the integral part is 6. So we have to note down this integral part separately, whereas the integral part, the fractional part, we will use to multiply it with again with the base. But now in this case, as we can see that the fractional part becomes 0 in the very first step, so no need to multiply it. Even if you multiply, it will become 0. So because 0 into 8 will be 0 again, so no need to multiply. So that's why we stop. The octal equivalent, therefore, of this 0.75 will be equal to 0.6 in base 8. Therefore, the total octal equivalent of the given number 73.75 will be equal to 111, which is the octal equivalent of 73, and 0.6. So the total equivalent is 111.6. The procedure was same, only the numbers used for as the divisor is different. It depends upon the base in which we want the answer. Similarly, the procedure to convert the fractional part was also same, just we have to change the base. So if we remember the general method, we can convert the given decimal number into any base, any required base. Now let's see the same example in hexadecimal system. The similar type of example in hexadecimal system. The given number is 82.25 and we have to convert this 82.25, which is given in decimal number, into hexadecimal equivalent. So we have to find the hexadecimal number which is equivalent to 82.25 in decimal number. To do the division, to convert it, to represent the equivalent number, the procedure which we will use here will again be same, but the divisor will change, and the divisor in this case will become 16 because the answer is required in hexadecimal number. So dividing 82 with 16 gives us 2 as the remainder and the new quotient as 5. Now, because 16 5s are 80, so 2 is the remainder and 5 is our new quotient. Now, as 5 is less than 16, we will stop dividing and this 5 will be noted down here. Therefore, the hexadecimal equivalent of the integral part 82 will be 52. Should be written in this order, not this order. So if you write it in this order, it will become 25, which will be wrong. The correct answer will be 52. So 52. So 5 2 is returned. So the hexadecimal equivalent of 82 is 5 2. Whereas for the fractional part, we have to multiply the fractional part with the radix, the desired radix, the radix of the desired number system. So 0.25 when multiplied with 16 gives us 4. So 4 becomes, which is 4.0. So 0, which is the fractional part, will be left here, whereas the integral part we have to note it down separately. So we take 4 here and 0. So now in the next step we have to multiply this remaining fractional part with the base again. But as the remaining fractional part is 0, so by multiplying this remaining fractional part with 16, the answer again will be 0. So no need to multiply it, and therefore we can write the total hexadecimal equivalent of 82.25 in the base 10 as 52.4 in the base 16. So this is the correct way. The method again is same, but the radix changes. Now moving on to the quiz, I expect you to solve this question by your own. So you pause the video and try to solve this question. The question is as follows. Assume an arbitrary number system having a radix of 5 and 0, 1, 2, L and M as its independent digits. Determine the decimal equivalent of 1 to LM. Point L1. Part B of the quiz is the total number of possible 4-digit combinations in this arbitrary number system. So you pause the video and solve this. I will show you the answer of this quiz in the doubt class. So you have to solve this question and have to show me in the doubt class. Thank you for listening this video. I'll continue the remaining part of the lecture in the next video. Thank you.